Hi all. So this talk is going to be a bit unusual in terms of the talks that I gave before, because I'm going to give a bit more details, not only what PSyclone does in LFRic scientifically and from the performance point of view, but also how do you work with code generation tool from the aspects of build system and code management and so on. All right. Okay, so just the clarification of terms to start with for the people who don't know. LFRic is the new weather and climate modeling system developed by the UK MetOffice to replace the existing unified model in preparation for the exascale computing in the 2020s. Uses the new Ganko dynamical core, which is a finite element based and runs on a semi-structured cube sphere mesh, which is a major change from the current unified model fully structured mesh. PSyclone is a domain-specific compiler and source-to-source translator for use in finite element, finite volume, and finite difference codes. Why am I mentioning all this? Because for the people who don't know, PSyclone not only works in the finite element LFRic code, it also works with, for instance, finite difference in NEMO. It uses the information from a supported API. Two examples that I said are the LFRic API and the NEMO API to generate code exploiting different parallel programming models. So this slide basically illustrates what we're trying to do here in the Met Office in developing this new weather model. So the unified model uses the endgame dynamical core, which is written in staggered finite differences, and it works on a fully structured lat-long mesh. The optimizations are hard-coded in the scientific code, which makes any kind of porting or adjustment for a new architecture quite difficult. Whereas the principle of design for LFRic and Ganko dynamical core are the horizontally unstructured, vertically structured quasi-uniform mesh, mixed finite elements, and for the ease of portability for the performance portability generated optimizations. As I said before, PSyclone is a domain-specific compiler for embedded DSLs. As I mentioned, it's configurable. It works for the finite difference, finite volume-based NEMO, GOcean, and the finite elements-based LFRic. So we are currently doing Fortran to Fortran and OpenCL. We support distributed and shared memory parallelism, and it supports code generation and code transformation. So PSyclone is a tool for use by HPC experts, and in a sense, it records the knowledge and the best practices of the HPC experts, and which, at least in the case from the Met Office, have a lot of input in the design of the desired features in PSyclone. So the optimizations are encoded as a recipe rather than baked into the scientific code. We are currently operating PSyclone with the CPU support for CPU optimization support for LFRic, and we are working on the GPU support. So a brief intro what PSyclone does in LFRic and how more specifically. So as perhaps I mentioned in the previous presentation, and just to repeat, LFRic basically works on the so-called separation of concerns between the science and code optimizations. So we have the cycle-light structure of the code, where AL stands for algorithms, which are natural science operations on whole data structures. For instance, what we call fields in LFRic. To just take a step back, the UM is operating on a structured mesh. So its data structures can be fully described by the Fortran arrays. Because we are operating on a horizontally unstructured mesh in LFRic, we need to carry a lot of information with us. what are the IDs of the mesh on the global mesh, on the partition, the connectivities between them, the mappings, and so on. And hence we are implementing data structures as objects that contain the data and the operations that access data, pack them, unpack them, and so on. And that is and that is supported by the LFRic infrastructure shown at the bottom right on this slide, which does all of it, and it also provides support for parallelism. Then in the so at the bottom layer, we have kernels, which are again natural science code, which do operations on columns of data points. I mentioned that the mesh is semi-structured, so we have direct addressing in the vertical and hence operating on columns. And in the middle is the parallel systems layer, which is the computational science, where the optimizations are applied and the data are unpacked from the algorithm and passed into kernels when they are updated. And this is where PSyclone comes in. PSyclone literally means cloning of the Psi layer. So how does PSyclone know what to do? We have this, we write our algorithms in this DSL embedded in Fortran, and it's written in Fortran 2003. As you can see, there is no actual mention or any kind of insight into what the data layout looks in the algorithm layer. The fields and other data structures are updated by the kernels, as I mentioned, and the kernels are grouped into these invoke calls, which is DSL. It is a pseudo Fortran and needs to be processed by PSyclone before it's compiled. Then in the kernels, the information that PSyclone actually needs to know is what object it is working on. For instance, these are the fields. What data type is it working on? And most importantly are these two last metadata in this archetype, which is the access, that is whether a field needs to be updated or just read from. And the very important one, which is the continuity of the function space, which in a data layout speak means that we either share data points between cells, and we need to be careful how to update them, which are the continuous function spaces, or we don't, which are the discontinuous function spaces. How does it all work? So in the top layer, we have this algorithm code, which I showed an example of, and the kernel metadata. That lives in the repository. The algorithm code lives in the repository, but it's not compiled per se. It needs to be processed by PSyclone. So what PSyclone does, it processes the algorithm code, it generates the algorithm code, which is then compiled, and where the invoke keyword is replaced by the calls to the invoke subroutines. The invoke subroutines then live in the generated Psi layer code. And this is where the translation between the algorithm layer and the kernel layer happens. As I said before, the data are unpacked, and we also apply optimizations such as distributed memory parallelism and shared memory parallelism. Shared memory parallelism is applied by PSyclone directly with the support of the LFRic infrastructure when it comes to continuous function spaces. We basically need the coloring algorithm to make sure that the data are updated as they should be. If they are shared DOFs, whereas for the discontinuous functions spaces, shared memory parallelism, OpenMP, for instance, supplied by PSyclone is enough. And also there are generated calls for the distributed memory parallelism, which is in turn provided by LFRic infrastructure that uses the YAXT library. And all in all, the optimizations from PSyclone are applied via the Python optimization script. So the rules of engagement here is that the LFRic gives the rules on how the data layout and how the data are to be accessed. And LFRic API in PSyclone takes those rules and generates the calls to infrastructure, how to unpack the data and parallelize them. If we don't have a functionality for PSyclone, we use SycleLite, which is the required PsyLayer functionality, which is handwritten, and this is the development tool and the template and the stopgap at the same time for the development of the necessary PSyclone functionality. So how does the development work? LFRic and PSyclone are basically developing in parallel, because as the science develops in LFRic, we need to produce the adequate PSyclone support. So we first gather science and performance requirement for the PSyclone support. In most of the cases, it needs the LFRic infrastructure support, so that is developed first. Then we write the SycleLite code, which I mentioned as a template and as a development tool for the PSyclone developers to look at what they need to do. Then the relevant code is developed and tested in a PSyclone side. So we test the code generation and the compilation. We do have about 99.5 test coverage in PSyclone repository, but we still have some occasional bugs between releases that need to be fixed. We also test the support in LFRic. We have the PSyclone test environments built from the later master or branch. If we're developing something in PSyclone, that can be used in the LFRic build system to test the support and so on. When we're ready, we release a new PSyclone, we integrate it in the LFRic software stack, remove the unnecessary SycleLite code, and so on. So this is just a brief summary of what I already showed on 2 slides before, which I wanted to actually highlight that this is non-classical approach to compilation, in a sense that we have code in the repository, the algorithm code, which is there, but it's not compiled. And we also need to generate the code, the algorithm code and the PsyLayer code, which is not in the repository and needs to be compiled. And we signal to the LFRic build system what needs to be pre-processed by PSyclone by this X90 extension. So what does it all mean for the management of PSyclone at the MetOffice? Well, first of all, we need to build generated code that is not in the repository, which is quite different from the current practice with the and similar codes. So the MetOffice is developing this fab build system that is also taking the code generation into the entire build process. Then, as we ramp up the use of PSyclone in the NEMO Ocean model and the adjoint and different implementations, we will likely need different projects with different PSyclone releases with different projects. So we need to think about that as well. Then we are in the middle of the porting to Gen 1 architecture. Gen 2 is going to be later. So it basically means that we need to think about how we manage the releases and software stack and so on. And I already mentioned the continuous testing of LFRic code against PSyclone master, and this is done so we catch as many bugs as we can between the releases. Occasional bugs still happen, and we have a very good collaboration between STFC and the MetOffice, which basically means that we can catch it all at quite an early stage and fix it. So a couple of highlights that I want to show regarding the use of PSyclone. One of them is the mixed precision, the implementation of mixed precision and iFirst data layout in LFRic atmosphere. So we have done a lot of work on PSyclone and LFRic infrastructure side for the support for the application of mixed precision in the science code in LFRic, and we also did work on the fields and operators of different data types. And the iFirst is basically to interface the existing parameterization schemes between LFRic and the unified model. So we have these big kernels which interface the physics, the Socrates for the radiative transfer, Joule's line surface model, and on. And they have radically different data layout. As I said, in LFRic, in Gung-Ho dynamical core, we are operating over columns, and the physics schemes, quite a few of them are doing the operations over the horizontal. So what we have implemented in LFRic infrastructure and PSyclone is the so-called domain kernels, which pass not columns of data to a kernel, but entire field, for the parameterization schemes to operate on them. As I said, the physics has same operation within a horizontal layer. These slides are the courtesy of Ben Shipway from the UK MetOffice. And for the iFirst structure, what we do in the kernel call. So we, in this iFirst kernels, we convert the data to whole domain iFirst data. We call the scheme on the whole domain, and we convert data back to LFRic. Whereas with the K-first kernel, which we usually use for dynamic, we would just call scheme on a column. So now we have the ability to do it on the entire field as it's done in the And there's our summary results. So on the top one are the solver precision results. So these are the, trunk is the LFRic trunk as a certain revision. And there are results with different number of OMP threads and on different number of nodes. And as it can be seen from the results, again, courtesy of Ben, that the 32-bit implementation of precision leads to quite good performance gains. The difference between trunk and 64-bit branch are the improvement in science, not in precision. And I already mentioned the physics and the iFirst work. And again, there are results for two different science configuration for the iFirst microphysics. And as you can see with the implementation of the iFirst looping and passing the fields to kernels, the calls of the microphysics are the timings are improved a lot. So we are also working on the application on the change of the coloring algorithm that we have in LFRic. And this is the work that is done by Wolfgang Hayek from NIWA. I don't think I will have time to go into them, but the slides are going to be available to all, so please have a look at them and ask any questions that you have to either Wolfgang or I am happy to put you in contact with him. So that would be it from me. Thank you.